This video will look at pH and titration curves. It's question 11b from the 2018 Leaving Cert. Alright, the first part of it there, I'm going to let you just look at the answer there yourself, and it's theory that you should have got from your notes or book. Alright, okay, at this stage you should know what an Arrhenius base is and why NH3 would be considered to be a Bronsted Lowry base. Okay, what we're going to look at is the second part of the question, relating to pH and then the titration curve there at the end. For this part, alright, calculate the pH value of a 0.5 molar solution of hydrochloric acid. Now we know that hydrochloric acid is a strong acid, so we're able to use the most simple formula that we have for pH, which is pH is equal to minus log, you can put into the base 10 of H plus. Okay, make sure we have our square brackets, otherwise you'll lose marks. Okay, so that simply is just going to be minus log of 0.5, and the answer there we get is 0.3. Okay, so the pH value of our hydrochloric acid is 0.3. Then for ethanoic acid, right, it gives us the acid dissociation constant there, Ka, because ethanoic acid is a weak acid. Okay, we use a slightly different formula when we are looking for the pH of a weak acid. The formula that we use will be pH is equal to minus log, okay, of the square root of the dissociation constant multiplied by the concentration of the acid. Okay, yep, so anything representing concentration of the acid will be fine for that symbol as long as you use the figure for the concentration. Okay, so that's going to come out to be pH is equal to minus log Ka, given in the question, was 1.8 by 10 to the minus 5, and we're going to multiply that by 0.5, and the pH value we get for our ethanoic acid is 2.52. Okay, so we'll just fill these in up here just so we can see them a bit easier. So this is going to be 0.3 and this is 2.52. Now, the next part of the question is the pH curve shown was obtained when 100 centimeters cubed of sodium hydroxide solution were gradually added to 50 centimeters cubed of one of the two solutions mentioned above. Okay, which of the two acid solutions was neutralized? Okay, from our graph, which is volume of your sodium hydroxide versus pH. Right, at the start we have no sodium hydroxide, so this here at 0 is just the acid, and we can see that our starting pH is about 2.5. So that means that our acid here, for the first part of the question, is the ethanoic acid. Okay, so our pH here, starting pH is 2.52, so this is ethanoic acid that is being neutralized. Another piece of evidence that we have is that the vertical line in the center of your graph there, that most of that line is actually above the pH of 7. Okay, so we're titrating a weak acid, ethanoic acid, against a strong base. Okay, if we were titrating a strong acid, if we were titrating hydrochloric acid, for example, against the NaOH, there would be about an equal amount of that vertical line above and below 7. Because we have ethanoic acid and NaOH, most of this vertical line in the center is actually above the pH of 7. So pH 7 is there. We have very little of this vertical line above or below 7, whereas the majority of it is actually above 7. Okay. If you were titrating hydrochloric acid against NaOH, there would be roughly an equal amount of that vertical line between the two. Okay. Alright. Okay, and then what is an essential property of an indicator used to detect the endpoint in a titration between this acid and NaOH? Okay, you need an indicator that will work in between the ranges, or in between the range of when that graph is vertical. So if we look at when that graph is vertical, it's vertical between about 6, okay, 6 and 11. Okay, so you need an indicator that will work in those, in that range. Okay, so methyl orange definitely won't work, and litmus wouldn't be the best either. Okay, so phenolphthalein would probably be the best one there because its range is between 8 and 10. Okay, but as long as the range of the indicator is along that straight line, then it is a suitable indicator.